Welcome to our 21 days masterclass series on autonomous vehicle. Today is day 70. I welcome you all for engage your learning experience with Pantech e-learning anytime, anywhere, at any places. We are always supporting to the students in a technical way. And our main vision to help the 10 million students easily learn the technology. So in our last session, we discussed how to simulate the vehicle parking maneuver in a driving scenario. And we have explored create a scenario and add the vehicle into that. And also we have to create a target vehicle in that parking lot scenario. So today in this session, we will discuss even more interesting things, adding ultrasonic sensors into that ego vehicle in a parking driving scenario. So let's do that one. I'm going to open the MATLAB software here. Just a minute. So in this example, you have to simulate an ego vehicle. It has a 12 ultrasonic sensor. So this sensor, it has a maximum range of 5.5 meters and this horizontal field of view is a 60 degree and the elevation field of view is 35 degree. So I am going to give the information through this MATLAB command window. So first, we use the number of ultrasonic sensor is a 12. So we have to ensure that one. So this one is indicating there are 12 ultrasonic sensors in the ego vehicle. And we have to specify the sensors and sensors equal of cell. Inside this cell, one command number ultrasonics. So this cell array that's named as a sensor, we have to initialize and this array will hold the sensor object. So the size of the array is set to 1 cross 12. That means 12 elements to accommodate that 12 sensors. So next we have to give the mounting locations. So this line, it defines the mounting locations for the each sensor. So it creates one kind of a matrix mounting locations where each row represents the particular x and y z coordinate of the mounting location sensor. Mounting location for the 12 sensors. So we have to give the mounting angles also. So similar to the mounting locations, this line, it defines a angle, that means orientation angle. So what is that orientation angle? Yaw angle or a pitch angle or a roll. So for the 12 sensor, 12 ultrasonic sensor. So it creates a matrix mounting angles where each row represents the angle for the sensor. So next we have to create all the sensors. For that I am using the for loop here. So inside this loop it creates a sensor object and assign them to the new sensor cell array. So within that loop we mention the ultrasonic detections generator and also the sensor index and mounting locations and mounting angles and field of view. So field of view is 60, 35. So it representing the horizontal and elevation field of view. So each sensor is stored in the sensor cell array at the index that corresponding to its position in that loop. So next we create the profile. So we have to register the actor profile within that sensor. So this line, it creates an actor profile from that scenario. So this actor profile, it defines the characteristics of the various objects. That means the various actors in that simulation environment. So we inside this loop, for loop, so M, we have to specify the M. So that means this allows the sensor to simulate the detecting objects with the various properties that defined in the actor's profile. And we have to mention the sensor color also. So what does this mean, sensor color? So this line, it defines the color for the sensor. So this color is specified in the RGB triplet. So that is normalized to the range between 0 and 1. So why we choose this value? So here we have the locations value and angles value. So mounting locations and mounting angles value. So these values are determined where the sensors are placed on the vehicle, how they are oriented. So mounting locations and mounting angles, these values chosen based on the physical constraints of the vehicle. So such as the available space and also the optimal coverage area for that particular sensor. So these values might have been chosen to evenly distribute the sensors around the vehicle. So it provides the good coverage of the surrounding environment also. So next one, the field of view. So field of view means it determines the angle over which the sensor it can detect the objects. So values for the field of view, it's chosen based on the specific requirements of that application. So suppose, for example, wider field of view in the sense might be preferred for the detecting objects in a larger area, while narrower field of view in the sense might be chosen for more focused detection. So here we specify is the 60, 35. That means 60 for the horizontal and 35 for the elevation. So might have been chosen based on the desired coverage and resolution, especially for the 12 ultrasonic sensor. So next we have to create another one more window here. So that is a BEP. So before we get into that, so why we use ultrasonic sensors here? So we know these ultrasonic sensors are commonly used for the distance measurement only, because they emit the high frequency sound waves and measure it takes of times for the waves to reflect of an object and return to the sensor. So this enables accurate distance measurement without physical contact. So ultrasonic sensors operate without physical contact with the objects they are sensing. So which is a very advantageous one in we use in applications like autonomous vehicles. So next one, this ultrasonic sensors, it has a wide detection range. So it can detect the objects relatively long distances compared to the other type of the sensor. So this makes them suitable for the applications where the sensing over larger distance is required. So next one, it's also cost effectiveness. These ultrasonic sensors are a very cost effective compared to the some other type of the sensor with the same similar capabilities also. So it is a very important to note that ultrasonic sensors may not be suitable for the all application, but they have also some limitations. But here we are using for the distance measurement in this simple parking valet system. So next we have to visualize that scenario. So for that we have to create this BEP by using this create demo display. So what does this mean? So this create demo display, this function, it creates a 3 planes. So what are the planes? Top left plane and also the bottom left plane and also the right plane. So first we have to create a figure for that and we have to give the name for that. So what is the name here? That is a parking maneuver scenario. So we have to give that name and we have to get the scenario time also. We are using this scenario dot simulation time. So next we have to create the 2 panels within that. We have to add the car plot and also we have to add the chase plot view and finally we have to add the bird's eye plot also. So finally we are going to plotting the sensor coverage by using this SNTX1 is to length of sensors. So this means it creates this loop, it plots the coverage area for each ultrasonic sensors on the bird eye plot. So it creates one kind of the coverage area plotter with the some specified space and also the edge color. So then the plots of the coverage area based on the sensor parameters. So we have to add the other plotters also. So what are the plotter we have to add? Yeah, so we have to add other plotters also. Just a minute. Yeah. So we have to add the range detection plotter and we have to add the lane boundary plotter and we have to add the lane marking plotter also. So finally, we are giving the axis properties to this sensor. So this line, it sets the axis properties for the bird's eye plot to make sure the aspect ratio is equal to the defined x and y limits. So finally, this function BEP, it returns a handle to the bird's eye plot. So next we have to simulate the scenario. So for the simulating scenario, we have to use this code here. So simulate the scenario. So we use the while function here. So this while function, this initiates a while loop. This loop, it continues as long as 2 conditions are met simultaneously. So what are the 2 conditions? One is a scenario and another one is a BEP dot parent. So this advanced scenario, this function, it advances the scenario by one time step. So if the scenario cannot be advanced, so for example, if the simulation has reached its end in the sense, this condition will evaluate to the false. So at the time the loop will exit. So the same, this function is HG handle function, checks if the parent graphics handle of the bird's eye plot is still valid, if the associated figure window has been closed. So this condition will evaluate to the false and the loop will exit. So next we have to use this scenario time. So this line, it retrieves the current simulation time from that scenario and assign to the new variable. So next is the poses. So we have to use this poses, target poses function, and this line, it calculates the position of the other vehicles that is relative to the ego vehicle coordinate. So mainly this target poses function, it's likely computes the positions of the other vehicles based on the ego vehicle position and also the orientation. So next we have to use the detections and field of views and locations and angles. So simulate the sensors. So detection in the sense, it's a empty simple cell array to store the sensor detections. And next one is the field of views. This is also one empty array to store the field of view of the sensor. And next one is the locations. So this array to store the mounting locations of the sensor. Next one is the angles. So this one, it store the mounting angles for the sensor. So next is the valid time. So this initialized to false, which will be used to indicate whether the sensor generated valid detections at the current time step. So next we use this for loop here. So this loop, it iterates over the each sensors in the cell array. So inside this loop, this line calls the sensor simulation function for the current sensor, that means the SNDX, with the position of the other vehicles also. One is a poses, another one is the current simulation time. So it retrieves the two outputs. So what are the two outputs? One is the sensor states and valid time. So sensors detection in the sense, it's generated by the current sensor, and this one valid time of SNDX, it's one kind of the logical value that indicating whether the sensor generated the valid detection at this current time step. So this values is stored in the valid time array at the index SNDX. So next we use this if function here. So inside this loop, the block of the code, it checks if the sensor data variable is not empty. So that indicating the sensor generated detection at the current time step. So if detections are present in the sense, it appends them to the detection cell array and store it in an additional information that is related to the sensor. So what is the additional information? So field of view and also the mounting locations and also the mounting angles. So next we updated the bird's eye plot. So after this loop, this code, it checks if any of the sensors generated valid detection at this current time step. So if at least one sensor has valid detection in the sense, so this valid is true, this is valid time is true. So it calls the updated BEP function to update the bird's eye plot with the new detections. So this entire loop, we have to use this update BEP function. So this update BEP function is responsible for updating the bird's eye plot. So with the new information that is obtained from the scenario and also the sensor detection. So next we have to update the road boundaries and also the lane marking. So we use the function. So we use this create demo display function, and also we use this update BEP function, and also we use this ground. So we ensure update the ground truth data also. So without this one, we can't run our simulation. So without this helper functions, we can't run the simulation. So update the ground truth data in the sense, this code, it retrieves the ground truth data. What are the ground truth data? It's a position and it's an angle and it's a length and it's a width and also the origin offset and color for the target also. So next we have to update the road boundaries. So this code, it update the road boundaries on the bird's eye plot. So finally, prepare and update the detection display.